In this video, I'm going to develop the idea of entropy to help us to calculate whether reactions are spontaneous at a particular temperature or non-spontaneous at a particular temperature. You sometimes might see the word feasible being used instead of spontaneous. They are interchangeable. So the first thing we need to do is say, well, what do we mean by a spontaneous process? And you can see there I've written up the definition for a spontaneous process. So spontaneous processes are processes which occurs without a continuous supply of energy. So I'm going to illustrate that now with the reaction that takes place when you use this gas lighter. So we've got butane inside the lighter, and when we get the reaction to go, it's going to react with the oxygen in the air and make carbon dioxide and water. And the enthalpy profile diagram for this reaction would look something like this. And so we'll just illustrate this business of spontaneous process now. So if I release the butane into the air in the lab, there is no flame. The reaction's not actually happening. And that's because we have to achieve or overcome this activation energy. So this is where students sometimes get this idea sort of wrong in their heads. They think a spontaneous process, using this combustion as an example, they just think that spontaneous means it'll spontaneously combust into flames. And of course it doesn't. So we overcome the activation energy barrier. The reaction's taking place now, but because I'm not constantly having to spark the lighter, the reaction is spontaneous because it doesn't need this continuous supply of energy. So you can see from the enthalpy profile diagram and the fact that we had a flame from the lighter, it's an exothermic reaction, and the driving force, if you like, for this reaction is this drop in enthalpy. So I sometimes visualize it a bit like a waterfall or something like that, or a cascade. As soon as you overcome the activation energy barrier, then the reaction sort of naturally wants to take that route and creates the spontaneity of the reaction. That's how I sort of visualize it in my head. So if we think about this reaction now, so this is ammonium nitrate solid. If we put that in water and just leave it, it will dissolve into its ions. So it doesn't need a continuous supply of energy, so it's a spontaneous reaction. The weird thing about this one is, there's its enthalpy profile diagram. This is an endothermic reaction. So if you think about that cascade or waterfall analogy that I gave you in the exothermic reaction, this is when this concept starts to seem a bit strange, because you're thinking, well, to get this reaction to happen, surely you have to give it a constant supply of energy to raise the enthalpy of the substances in the equation. So what is it that makes this process spontaneous when if you look at the enthalpy diagram, surely it needs this helping hand, if you like. And so here's the link with entropy now. You can see I've written up there, entropy is a driving force too. So if we think about the entropies involved in the equation, we've got solid. Remember, solids have relatively low entropies. So this solid, when it's put into water, is turning into aqueous ions. So there's more disorder on this side because these have more freedom of movement. And so the driving force for this reaction, well, can't be the enthalpy, because we have to lift the enthalpy up to turn the reactants into these products. But the fact that it's getting more disordered is driving the reaction. And so this would have a positive entropy change, and that's what's making this endothermic reaction spontaneous. So we're now going to use our knowledge of entropy and enthalpy to explain why ice doesn't melt until 0 degrees C. And to do that, I need to introduce you to a concept known as the Gibbs free energy, or delta G for short. So if we think about chemical reactions and we think about the energy from the reaction, we need to be aware of the fact that it can't all be used to do useful work. So some of that energy involved in the reaction is actually used to change the entropy of the substances involved. Once that's been done, if there's energy left over, then that can be used to do useful work. And we call this leftover energy free energy, and because the scientist involved was called Gibbs, it's called the Gibbs free energy. So in a moment we're going to do a calculation to work out the delta G for a reaction, and you can see I've written up there a negative delta G means that there is energy left over. So for a reaction to be spontaneous at a particular temperature, we've got to have a negative delta G. So before we can answer the question about why doesn't ice melt until 0 Celsius, I need to introduce you to the Gibbs equation now, which is delta G equals delta H minus T delta S. So if we look at the terms in the equation, this is obviously the Gibbs free energy. And remember, we want that to be negative, and then the reaction is spontaneous at the temperature involved. The delta H is the enthalpy change, the T is the temperature, and the delta S is the entropy change. Now, he said enthalpy there. Now, straight away, if we're not careful, we could run into some problems with this equation. So you can see I've written up the units for delta H, temperature, and delta S. So the first point I want to make is delta H, typically kilojoules per mole, and delta S is joules per Kelvin per mole. So we've got kilojoules and joules. So what you have to do is you need to work in the same units, if you like. So I tend to put everything into kilojoules. You can work in joules if you want, but normally delta G is expressed in kilojoules per mole, and so I turn everything into kilojoules per mole. So you would need to divide your entropy value by 1,000 to get the joules per Kelvin per mole into kilojoules per Kelvin per mole. So that's the first thing. The second thing is to do with the temperature. You can see there we've got Kelvin for temperature. You can see K there. So we've got Kelvin here. So we've got to be consistent with these units, and so we use the Kelvin scale. And if I just make this point as well, if you think about 0 Celsius, if you had a 0 there, that would completely just wipe that term out, which you don't want. And so we've got to work in Kelvin. So I'll just do a couple of examples now. How do you convert Celsius into Kelvin? And then we'll move into saying why ice melts at 0 Celsius and not anything lower than that. So if we take our friend the standard temperature, so we know from enthalpy chemistry that the standard temperature is 25 degrees C, which is the same as 298 Kelvin. And so what's the difference between these two? It's 273. So to go from Celsius to Kelvin, we add 273. So if we go in the other way, Kelvin to Celsius, we subtract 273. So that's why the absolute 0, so 0 Kelvin, is minus 273 degrees Celsius. So we've finally got round to the ice to water question now. So you can see there's the equation for the melting of ice, and I'm telling you that the delta H for the process is 6.03 kilojoules per mole, and the entropy change is 22.1 joules per Kelvin per mole. So what I want you to do is work out delta G at a temperature of minus 1 degrees C. So in your head you know ice won't melt at -1. Let's use delta G to explain why. So if you pause the video and work that out. So hopefully you got the same delta G as me. I got 0.0188 kilojoules per mole. So I've put everything into kilojoules. So that was in kilojoules. I left the delta H. The delta S, I divided this by 1,000. So knock the decimal place back 3. 1, 2, 3. 0.0221. And the temperature -1 Celsius would be 272 Kelvin. And that gives us this value here for delta G. The important thing is the fact that it's positive. So positive delta G means this reaction is not spontaneous at this temperature. Now what you can do, change the temperature to 0 Celsius and let's see what we get. So you can see on the right hand side there's the calculation for 0 Celsius. The delta H and delta S don't change. The only thing that's changed is the temperature's gone from 272 to 273. And the important thing is the fact that we've now got a minus sign in front of our delta G answer. The fact that this is the first temperature at which the delta G goes to negative, that means that that's the magic temperature, if you like, whereby this process becomes feasible. So ice melts at 0 Celsius because delta G is less than 0.